In this lecture, we'll do an improvement to the design of our processor by introducing the concept of pipelining. The concept of pipeline is very important in computer architecture, and if you continue studying computer architecture, you'll become very familiar with pipelining. All modern processors execute in a pipelined fashion. So the idea of pipelining is very familiar to you already. It's the idea of an assembly line. To introduce the idea of pipelining, we'll consider an analogy. And this analogy considers the task of doing laundry. And let's suppose that we can divide the task of doing laundry in 4 different stages. In the first stage, we run the clothes through the washer. The second stage, we run through the dryer. Then we have a folding stage, and then we have the stage of putting the clothes away. So one possibility that, and let's consider that we are one of our 229 students and that we are very busy with assignments and homeworks and labs and everything, and we don't have time to do our laundry very often, so our laundry accumulates, and when it's laundry day, we have lots of laundry to do. So on laundry day, let's say that we start at 6 p.m. and if I do one load of laundry in that fashion, I'm going to finish my first load by 8 p.m. And by 8 p.m. I can start my second load of laundry, which will finish by 10 p.m. And then I can start a third load at 10 p.m. and I will be doing laundry until midnight. And then I will finish my laundry at 2 a.m. And that will be a very busy night where I cannot do much else. Now let's consider that I take a look at this and I say, no, but I can do better. What I'm going to do is I will do the washing, the dryer, and drying, folding, and putting away of one load. But while I'm doing the drying of the first load, I'm going to be doing the washing of the second load, and then I can be doing the folding of the first load, the drying of the second, and the washing of the third, and then I can be putting away, or maybe I have a friend putting away, but there is the putting away of the first at the same time that I do the folding of the second is happening, the drying of the third, and the washing of the fourth. So this is the idea of the pipelining. We divided the task into 4 different stages in this case. And in the beginning, in the very first time that we start, we only have one thing happening, just the washing, because there are no clothes to dry. But when we get the second period of time, we already have 2 things to do. We can be drying the first load and washing the second, and so on. So this is the idea of pipelining. This idea is very common to everybody. We commonly employ this to do a number of different tasks. On cooking, on making a car, on fabricating a sweater, all kinds of human activities involve pipelining. We need to analyze our pipeline now and see how well we are doing. We want to know what is the speed up. The speed up, as we saw in our performance unit, is the quantification of how much faster a solution is compared with an alternative solution. So the speed up here will be how much faster can I do my laundry if I use this pipeline idea versus an operation where I do not do any pipelining. So to find that out, we also want to know, the 2 things that we want to know. What is the speed up if you have to do 4 loads of laundry, and what's the speed up if you have to do many loads of laundry? Because the pipeline will really pay off when I have many things to do. So if I have 4 loads, the speed up will be, I had the 4 loads to do. Without pipeline, it took 8 cycles for me, or 8 units of time for me to complete the task. And after pipelining, it takes 3.5 units of time to complete the task, so the speed up is 2.3. However, if I'm doing non-stop, which means that I'm doing many loads of laundry, then the speed up will be 2 times n. That's the amount of time that it takes for me to do n loads, because it takes half an hour for each load, divided by 0.5n, because when I'm executing this in pipeline, I can finish a load of laundry every half an hour. And there is this 1.5 that I need to add to the equation, because this is the time that it takes for me to fill up my pipeline in the beginning. So in the beginning, my pipeline is not completely busy. It's only at this cycle here that my pipeline is busy. And if I had many loads of laundry to do, then I would see the sequence of full pipeline happening. So in this case, my pipelined solution is 4 times faster than my non-pipelined solution. So the speed up is approximately equal the number of stages that I have in the pipeline, as long as each one of the stages takes the same amount of time. So let's consider the pipeline for our RISC-V processor. For our RISC-V processor, there are 5 stages in the pipeline, because remember, there are 5 stages for execution of a load instruction. And I do one step of instruction in each stage of the pipeline. So the first step was the fetch step, so I do instruction fetch. I call this the IF stage. Then I do decode, that's my instruction decode and read register stage. I call this my ID stage. Then I have the execution, that's when my arithmetic and logic unit does its operation. I call this the EX stage. Then I have the memory stage. That's the memory stage is where the load and the store instruction access memory. This is my mem stage. And finally, I have my write back stage. That is the one that write back the values to the registers. This is my WB stage. The performance of my pipeline, if I assume that the time for the stage is 100 picoseconds for register read or write. So if you wanted to put that in perspective, the light travels less than 3 centimeters during this time. Electrons are much slower than that. And here is a little side note. Sometimes it's hard for us to wrap our mind around what those speeds are. And there was a great scientist in the beginning of times, in the early times of computing science. Her name was Grace Hopper. And Grace Hopper was very concerned with performance. And she found it difficult to explain, as she puts in this short YouTube video that I recommend you watch. She found it very difficult to explain to mothers and fathers, grandmothers and grandfathers, and generals what time is like in a computer. So she had someone cut the amount of water that it takes for light to travel to in 1 nanosecond. And she called that the 1 nanosecond water. And her main point is that many engineers waste a nanosecond thinking that a nanosecond is nothing. And she wanted to show that a nanosecond is a lot of distance that light can travel during that time. Let's assume that, so in this case, we have 100 picoseconds for the register read or write stage, and we have 200 picoseconds for all the other stages. So if this is my design, I want now to compare the pipeline data path with the single cycle data path. So here's a table where let's try to understand this table. I have my different type of instructions. So I have a load, I have a store, I have my R format instruction that are all my arithmetic and logic unit instructions, such as add, subtraction, and all my logic instructions. And then I have my branch equal instruction. And what I wanted to look at here is the total amount of time that I take to execute each one of those instructions. Remember that different instructions execute different stages. So every instruction does fetching and decode. Then the load does an arithmetic and logic unit operation, a memory access, and a register write. So if I add all those times, the load will take 800 picoseconds. The store does not need to do the register write, because the store does not write to any register, so that's 700 picoseconds. The R format will require 600 picoseconds, because it does the fetch, the decode, the execution, and the register write. And the branch equal will take 500 picoseconds, because I do not need an extra cycle for the write back. I can take the value of the PC+4 or the target of the branch and send to the PC. So if I look at this table, I see that the instruction that takes the longest is the load. If I'm building a pipeline where the stages take different amount of time, the amount of time that I would have to wait between shifting things between stage is the maximum amount of time for any given instruction. So 800 picoseconds is the time that I need for the load. So now let's look at the performance of this pipeline. So without pipelining, I have that I'm going to have to wait 800 picoseconds for each instruction. The single cycle, if I do my design of my processor, where every instruction has to complete in a second cycle, the single cycle design here will be a clock cycle of 800 picoseconds. So this is the time to the completion between two consecutive instructions. I will do a load, and only then I'm going to start doing the next load. I'm not pipelining. Now, if I pipeline this execution, what's going to happen is that, remember that my instruction decode only takes 100 picoseconds. Well, I'm going to have to wait the other 100 picoseconds, because I needed to synchronize the execution of the instructions in this way. Therefore, now each one of my instructions will take 800 picoseconds to complete, regardless of how much time they actually needed in the previous table. But now that I have this, one thing that I can observe is that I can finish an instruction every 200 picoseconds. So I can reduce my clock cycle to 200 picoseconds if I consider a transition of clock at the end of each stage of the pipeline. So if all stages are balanced, so if they all take the same amount of time, the speed up because of the pipeline, that is the time between instructions that in the pipeline execution, is the time between the instruction non-pipeline divided by the number of stages. So if the pipeline is not balanced, which means that some stages take longer than other, the speed up will be less than that, because the speed up will be less than that because some stages are going to have to wait. Now, the speed up that I have in the pipeline is not because I increase latency, it is because I increase throughput. Throughput is the number of things that I can do per unit of time. So I can complete more instructions per unit of time, but the time that it takes for me to do a single instruction is the same as before. It does not decrease. Actually, in some designs, the time to complete a single instruction may be longer when you have the pipeline, because you need to have the coordination between the stages. A good way to understand that is to think about the construction, for example, of a car in an assembly line. And let's just stop for a minute and think that I have to produce two cars, a red car and a blue car. In the non-pipeline fashion, what is going to happen is that I start producing my blue car in the beginning of the line, and I don't do anything. The red car doesn't get started until the blue car goes to the end and gets out of the factory. And the time that it takes to produce the blue car is the difference in time between the time that it came out of the factory minus the time when it went into the factory. So that's the time, that's the latency to produce the blue car. Now, if I pipeline the production, what will going to happen is that the red car will be able to follow the blue car right through in this production line, and then I could have other cars coming afterwards. So the time that it takes to produce the blue car will not going to change. That's the latency. The time that takes to produce the red car will not going to change, that's the latency. But the time in between, so between finishing the blue car and finishing the red car in the pipeline fashion, in the pipeline design, the time is much smaller because it's just the time at one of the stages of the assembly line. So I can produce more cars per day, but it still takes the same amount of time to produce a single car. The same thing happens in the pipeline here in the processor design. So pipeline and instruction set architecture design. So the type of instructions that I have in a processor is affected by my pipeline design. So in the case of RISC-V, the instruction set architecture is designed for pipelining, to enable pipelining. One of the things that happens is that all the instructions are 32-bit, so that I have uniform instructions for decoding. It's easier to fetch and decode the instructions in one cycle. If we compare the x86, which is a widely used architecture, is the architecture from Intel, in the x86 you can have between 1 and 15 bytes per instructions. The instructions are not the same size. Actually, someone asked why we are using the RISC-V in 229 and why we switched it from MIPS. One of the main reasons that we switched is because of the proposal of RISC-V of being an open source architecture and the influence that RISC-V is likely to have in the next 10 to 20 years in computer architecture. MIPS is still a very good architecture, but MIPS is mostly used these days for embedded processing, and it goes into cars, into refrigerators, TVs, etc. RISC-V has a perspective of becoming much more popular and much more broadly used, including in serving computing in the future. And the reason we do not study x86 is because x86 is a very complex instruction set architecture and is not a very good architecture to be the first one that you learn. But in one of the complexities is the number of bytes per instruction in the x86 is variable. RISC-V has very few and very regular instruction formats. Even though you may think that all this immediate shuffling is very confusing, it still is a very regular instruction format. And one of the advantages of that is that you can decode and you can read the registers for an instruction in one cycle. This is not the case with more complex architectures. The other characteristic of RISC-V is that it is what we call a load store addressing machine. That's the reason why you cannot operate with a memory location when you are doing an arithmetic and logic unit instruction. For example, you cannot add a constant to a value that is in memory. You first need to bring the value from memory, you add the constant to it, and if you need it to be in memory, you write back to memory. Although this is the execution of more instructions, it makes the design much simpler. In machines where you can do an operation with memory, all that will have to be done by the hardware, making the hardware design more complex. So because it is a load store addressing, it can use the third stage of the pipeline, that is the execute stage, to compute the address of the memory that's accessed in the fourth stage. So this is the first part of this lecture. I'm going to stop here, and in the second part we're going to talk about hazards in the pipeline.